In this section, we're going to learn about how to take these, or how to find the solution to these differential equations that require a substitution. As we've seen, there are some very nice separable, linear, or even exact differential equations. Sometimes they don't fall into that category, and sometimes we can manipulate them into being one of the three types. So we're going to use a substitution, and I'm going to show you the techniques necessary to be able to do these. Unfortunately, substitution is more algebraically taxing than the previous types. So as we go through these, make sure you do pay close attention to the algebraic techniques as we go along. So we'll start off with a pretty easy example, and then we'll graduate to a little bit more difficult. So we want to solve x plus y quantity plus y prime equals x minus y. I don't think that there's any way that we can manipulate this into one of the other types. It's not exact. Before I even started this, I wanted to determine if it was exact. And if you take the partials, one's positive 1 and one's negative 1. So unfortunately, it doesn't work out too well for that. So here's what we're going to do. We're going to define a substitution. And usually the composite function is, if you would, is going to be equal to v. So in this case, x plus y. So I'm going to set v equal to x plus y. And that takes care of everything except for y prime. So what I'm going to do is, now remember, x is the independent variable in this case, and v is still going to be the dependent variable, and v is dependent upon x. So I'm going to write that up here. V is still dependent upon x. So we're going to solve this for y. So we know that y is equal to v minus x. And if we take the derivative of both sides to be able to substitute not just for y, but also for y prime is going to be equal to, we don't know what v is, but v is some function of x, and it's dependent upon it. So we're just going to call that dv dx. We could even call it v prime if you want. And the derivative of x with respect to x is 1. Right? So now we're going to perform the substitutions. Remember, we said x plus y is going to be equal to v. All right, so, and since it's our first time doing this, I'll make sure we go through this carefully. So this is v. In fact, let me just rewrite it so that way we can see it really explicitly. So x plus y times y prime is equal to x minus y. So this x plus y, that's v. Y prime is dv dx minus 1. X is x. And then y, we already said y was equal to v minus x. Alright, now you're probably looking at this and you're wondering, well, that made it even worse. How could this possibly have made it any better? Well, let's distribute the v on the left-hand side, and let's distribute the negative on the right-hand side. So we have v dv dx minus v. And if I distribute and combine like terms, I get a 2x and I get a minus v. Alright, now notice on both sides that we have a negative v, so if we add v to both sides, those are going to cancel, and now we get a really nice differential equation what's left over from this. And so we end up with v dv dx is equal to 2x. We can multiply both sides by dx because now this is a separable equation. Okay, so we can't forget that the whole goal of this is to perform a substitution so that we get one of the three other types. We're going to multiply by dx, and we get v dv equals 2x dx. Now we can integrate both sides with respect to dv and with respect to v and with respect to x. Antiderivative of v is v squared over 2. Antiderivative of 2x is going to be 2x squared over 2, or just x squared plus c. We can multiply by 2, so we get that v squared equals 2x squared plus 2c. We can back substitute for v. Remember that v was equal to x plus y. Okay. So we're going to get x plus y quantity square equals 2x squared plus 2c. And if we wanted to, we could find the explicit solution for this. So if we do so, we could take the square root of both sides. So x plus y is going to be equal to plus or minus square root of 2x squared plus 2c. And then finally, we're going to subtract x so we can get to that explicit general solution. So that's going to be negative x plus or minus the square root of 2x squared plus 2c. All right. Now, on a scale of 1 to 10 of rigor, this one was probably about a 1 or a 2. All right. So, unfortunately, they are going to get more rigorous algebraically and also with respect to the calculus. Let me show you a second example. All right. This is a prime example of a substitution problem. dy dx is going to be equal to tan of x plus y. So for anybody that's looking at this, I think it's pretty obvious as to what the substitution is going to be. Again, try to make that interior function equal to v. So in this case, our substitution v is going to be equal to x plus y. And we can use the exact same derivatives as well as the exact same manipulatives as last time. So we know that y is going to be equal to v minus x, and we know that the derivative dy dx is going to be equal to dv dx. Okay, so that's the derivative of v with respect to x minus 1. And now we're going to substitute. So dy dx, which is dv dx minus 1, so that's easy, equals tan of xy, and xy is equal to v. So we get tan square, of v. All right. Now, at this point, we have to decide what type of differential do we have. All right, and this one looks like it's going to be tough, but in fact, it doesn't work out to be all that bad. Because if we remember our trigonometric identities, particularly the Pythagorean identities, if we add 1 to both sides, we can rewrite this as dv dx is going to be equal to tan square v plus 1. And you might remember that tan square v plus 1 is a trigonometric identity. So we can rewrite that. dv dx is going to be equal to secant square of v. Now, that doesn't make it very easy, but at least it makes it at least integrable. Right? Now, to be able to solve this, it's going to be another separable differential, similar to the first one. So we have dv over sec square v is equal to dx, just by multiplying both sides by dx, dividing both sides by sec square. You may recall that the reciprocal of secant square is going to be equal to cosine square. All right, so we're going to rewrite this as cos square of v dv equals dx. Now, a trap that a lot of students will fall into is they try to integrate cosine squared. And what they'll do is they'll write cos cubed v over 3, all right, plus c. And that is not the correct antiderivative because it is not a polynomial. Remember, the power rule only works for polynomial expressions. So you might remember from Calculus 2, to be able to evaluate cosine square, you have to use a particular formula. You might remember the power reducing formula. Right? And this is one that we're going to use a lot throughout the course, and in fact throughout your mathematical careers. Remember that cos square of v can be written as 1/2 plus 1/2 cos of 2v. All right. And that's on that sheet. I think it's on the back of the unit circle. So make sure you have those, all right, at your disposal, so that way you can utilize those sorts of formulas. All right. So we're going to rewrite this as 1/2 plus 1/2 cos of 2v dv is going to be equal to dx. Okay. And now we can integrate both sides. And the integration isn't too terrible. Antiderivative of 1/2 with respect to v is going to be 1/2 v. Now, if this was a chain rule, then we would multiply by 2 because of the interior function. And remember, it only works for linear. If that was a v square, then we couldn't use this trick. However, because we're doing the reverse of the chain rule for derivatives, we are going to divide by 2. So this becomes 1/2 times antiderivative of cos is sine, and we're going to divide that by 2. All right, so it's the opposite of the chain rule. Antiderivative of dx is x, and then we have a plus c. We're going to back substitute now, and remember v was equal to x plus y, so this is 1/2 quantity x plus y plus 1/4 sine 2x plus y is equal to x plus c. All right. At this point, I don't think it's possible for us to even try to solve for y because of this sign. Right? So we would have to do an arc sine, but we'd also have this y to worry about. So at this point, we could leave it as such. If you wanted to distribute the 1/2, that's perfectly fine as well. All right, but let's just leave it in this form. We could even solve it for c, and then we could get a function if we wanted to, similar to how we did the exact equation. So one final way that we could write it is fxy, by setting it equal to c by subtracting x, would be equal to, now we have a 1/2 x and we're going to subtract x, so we're going to have 1/2 y minus 1/2 x, so this x and the 1/2 x we subtract from both sides, and then the rest of it stays the same, plus 1/4 sine of 2, and we could distribute the 2 to get 2x plus 2y. You could probably use one of the sum formulas on 2x, 2y to maybe rewrite the sine function. I think it would make it more difficult. All right, so that's just some different ways to be able to write it. This might be the most useful way to write this because it's a function of x and y, and you might be able to plot it on some sort of graph or online. And you could also start to be able to find derivatives of this sort of thing, just to be able to maybe work with this a little bit of the function itself. All right, so in the next videos we're going to take a look at some more difficult substitutions, or maybe even different, maybe not necessarily more difficult.